Hey guys, I figured I'd record a quick video just to help you guys out with post-lab questions number 4, 5, and 6. I want to take a look at the mathematical side of Graham's law. So we're going to get some values plugged in, figure out how to come up with a theoretical or kind of a known value for the ratio of velocities between our ammonia and our hydrochloric acid, and then also do the same thing but using our experimental data. And between 4 and 5, that should lead us to a nice error analysis in question number 6. So hopefully you'll find this useful. Here's the work that I've produced for question number 4. What we find is we have Graham's law first. So again, if I want to find the ratio of velocities between, say, gas A and gas B, I'm going to take a look at kind of the inverse square of these molecular weights, of these molar masses. And so the question asks, what is the ratio of the velocity of ammonia to hydrochloric acid? Okay, so if this is the ratio I'm looking to employ, I got to make sure that I set up that inverse square appropriately, right? So while I have my NH3 velocity up here in the numerator, I see that my numerator on the other side of things, I'm actually talking about hydrochloric acid, right? The hydrogen monochloride gas there, okay? So now that I have kind of the formula in hand, in order to find this ratio, which again is what the question's asking, is I merely plug in the molar masses. So using the periodic tables I distributed on day 1, which is the College Board approved periodic table, these are the molar masses I came up with. Okay, so I divide, I find the square root, and I get this really, really large number. Okay, and the reason we see so many decimals here is because I've not limited myself. Given that these are molar masses, we're going to assume that they're relatively precise. And right now, in our calculation, it's not going to look to limit us. Okay? Great. So this is going to be our kind of known or a theoretical value. This is to say that given that NH3 is a lighter gas than HCl, we would anticipate it having a higher velocity. And in fact, theoretically, it should travel 1.46 times faster. Okay, that's what this number is telling us. That its velocity is going to be 1.46 times the velocity of that HCl at the same temperature. Okay, so if we move on to question number 5, what we're now tasked with doing is figuring out the same ratio but using our experimental data. Okay, so I have here this kind of scenario where I have my NH3, I have the HCl, our precipitate or kind of our smoke ring formed, at these distances. So again, the NH3 has traveled a little bit further, the HCl maybe not as much, okay? So if these are the distances, what I've done is I figured out what the individual velocities are. So I've divided by the time on my timer there, okay, making sure that I'm talking about seconds. You'll notice the number of significant figures on the centimeter values here. The rulers we used in class today had gradations to the tenths, which is to say that we can record that value to the hundredths with relative, maybe not relative certainty, there's an uncertainty associated with it, but it is truly significant, okay? And the stopwatch was giving us values to the hundredths as far as the decimal goes there, okay? So centimeters per second, I calculate the individual velocities. And right now I've chosen not to round, right? So again, I'm gonna kind of save all that sig fig consideration towards my very final step. With these velocities in hand, again, the goal is to figure out that experimental ratio of the velocity of the NH3 to the velocity of the HCl. So plugging these values in to this equation, I arrive at 1.289902228, so on and so forth. And at this point, if I were to kind of truncate my answer, or if this is, kind of where I'd end things, I think this is what you come up with, right? It looks as though per the centimeters here, per those distances traveled, that's where we're truly limited to 4 sig figs, okay? So experimentally, we've determined that NH3 is moving 1.290 times faster than our HCl gas there, okay? So now that we have our known, or kind of our theoretical value in hand, and we also have our experimental value in hand, I want to do a quick error analysis. Okay? This should seem pretty familiar to you guys from a previous chemistry class. So what I have here is my governing equation, actual minus experimental. divided by actual, we're taking the absolute value of this, like Again, negative or positive in the numerator would kind of tell us whether we've overshot or undershot, relative to the, the theoretical amount. But this is going to shoot a decimal, so we multiply by 100 just to convert to a percentage. Okay. So if you recall back from a moment ago, this 1.4629, so on and so forth, that was our known value. We came up with that by using the molar masses. Okay. I've subtracted off my experimental, I divided by the actual, and multiplied by 100, and I get the following numbers here, okay, as far as like the numerator goes. Now, given that this is a subtraction step, this 1.290, again, we are limited to kind of 3 decimals at this point, 3 decimals, okay? And so, again, I haven't chosen to round yet, but really it'd be like 0.173, okay? This is a subtraction step. So we are limited to 3 places after the decimal here. A lot to keep track of. Okay? I do a final division step. I realize that because there should have been 3 sig figs here, and there's like this infinite number, we're limited to 3 sig figs. So I've chosen to round that final percentage to 11.8, and not too bad. 11.8, not too bad for percentage error there. Again, comparing the theoretical to the experimental ratio of velocities to NH3 and HCl. Hope you guys found this to be helpful. Thanks.